Hello guys, so today as promised we are going to see how to solve one way to solve the quantum harmonic oscillator. So we do quantum, so it will be some quantum mechanics, and then we know harmonic oscillator. Okay, so just to remember quickly, an harmonic oscillator in classical mechanics is an object, let's say a mass if you want, that exactly oscillate harmonically, meaning that his position in time draw like a sinusoid or cosinusoid, cosinus of omega t, for example, and this is time. So, and this is the position in time, okay? And usually, and we saw that the energy that this oscillator usually have are made of two components. One is the velocity squared, the kinetic energy, and the other is the potential energy. Maybe there is no factor of 2, but we can put a factor of 2 or not, depending on, okay, I don't remember. But it doesn't matter. The structure is a quadratic, it's a quadratic form, okay, sum of two squares. Now, last time I think I did a clear mistake, because when I introduced the operator A dagger and B dagger and A, sorry, and A, I wrote them like the operator momentum X plus P and X minus P. This leads to the correct commutation relations, I think, but the trick here is that they need to be written like this, with a complex value here, okay, complex unitary, imaginary unity there. And the reason because I'm doing this is actually a fundamental reason, is that if you remember the complex number Z, which is A plus IB, we can derive the complex conjugate Z star, which is A minus IB, okay? And for a reason that I'm not going to discuss in this video, maybe in later videos, but it's quite important, we usually deal with in quantum mechanics with function operators. These are operators, by the way. We know that they work on matrices or functions, and they need to have these properties. They need to be they need to be related by this adjoint operation, okay? And as you can see, A and A dagger, these two operators are exactly like one, the complex conjugate of the other. And this, as you can see, because there is the minus sign here, which is the same as here, right? So, and why this is important? Because last time we saw that our energy operator, the Hamiltonian, was A dagger times A plus some constant, which was an energy, h bar omega, okay, C equal h bar omega. So it's smallest energy, by the way, that you can have for one quantum of excitation of that system, okay? And yeah, so why this is important? Because now you can see that if you take A dagger A and then you do the complex conjugate of this, if you like, this will become the same as, it will will be the same, a again. We can do this calculation. Let's see if it turns out to be correct. So we do x plus ip, x minus ip. This is the first bit, and then we need to make it complex conjugate. Okay, so this is a bit annoying, but I need to say these things because they are quite important. So this is x squared plus p squared plus ipx minus ixp minus ixp, and then we take the complex conjugate of this. Okay, and then what happens? Yes. So x and p remain the same. So x squared remains x squared plus p squared remain the same, and this one swap the order and the sign, so minus ixp plus ixpx, which just by look at it is the same. They have the same structure, the same components inside. So actually this operator here is the same when you apply the complex conjugation. This is important because it means that it's in an operator that can be observed in a sense, meaning that the value of the value of this operator on any state, meaning when you take a measurement on your system and you want to measure this value of this quantity here, that will turn out to be a value that we can measure on a real scale, like real numbers. We study about real numbers, and they can be negative, positive, or we can count them. We can count them, yes, but we can approximate them as well. They can be rational and irrational, but what I'm saying is that they can be measurable number. Okay, so in fact this operator is called number operator, as we can see today, and it will give us the number of quanta of energy that are in the system for that particular instance in time. So I don't want, okay, I will just add a buzzword, but it's a fundamental word, which is this operator called self-adjoint, and they are ubiquitous in quantum mechanics because, as I said, the observable that usually we deal with are self-adjoint. X is self-adjoint, P is self-adjoint. In fact, they represent the position that we can measure and the momentum. The momentum is mass and velocity, so it's something that we can measure. The mass we can weight, the velocity we can time it. So linear momentum, anyway. Okay, so enough. So just remember that there is an I. If I forgot last time, it's important because these two are on the complex conjugate, the adjoint of the other, and this is important because when you put them together like this, you multiply them, they're self-adjoint, and you get an operator that is an observable. And we will see that this operator will count the number of excitations in our system. But let's see if I can be a bit more specific, a bit more clear. So we have an harmonic potential. An harmonic energy, which is made of, yes, but even an harmonic potential, because the potential is kappa x squared, which is the potential energy, which is the second bit of our equation here, which is this. But we know that these, we know already how to draw this in a sketch, because this is a parabola, okay, passing from 0. Okay, what does this tells us? It tells us that in the energy there maybe there is no maximum. You can keep adding energy to the system, but definitely there is a minimum. There is a 0 point. Okay, we can see here there is a 0 point, and below that we cannot go. And also there is a 0 point because the energy here is always positive, so we cannot go negative with the energy. So even the velocity cannot go below 0. So the least that you can do is 0 point, so the particle is not moving. Think about the pendulum, which is hanging on the wall. When your clock, for example, the cuckoo clock is done, because the battery or the mechanism is gone, it's standing there, right? So there is no motion, there is no velocity, so the x is fixed and v is fixed. So it's like the minimum potential energy that system can have. Otherwise, if you give some momentum, it will start oscillate back and forth, as we know with the harmonic with an harmonic behavior. Okay, now what happens? We know in classical mechanics what happens. Now we try to we try to use this operator A and Dagger, creation and annihilation operator, to solve our problem. So first of all, I will get rid of a few constants because I don't want to keep track of them. And let's say that our Hamiltonian can be written. So we remember that A plus IB times A minus IB. This is A square plus B square. We know that. So, and we know that then our Hamiltonian can be written because there is an I. This is important. Otherwise, there would be a minus there. And actually, I'm writing here down. If it's A plus B times A minus B without the complex conjugate, it would be like this. Okay. And this is important because our Hamiltonian is the sum of two squares, x squared plus a constant plus d squared plus p squared. Okay, meaning that we can write it with these two, basically we can write it like this, cx plus dp, and then we can write it cx with an I, cx minus I dp. Now the constant, I will drop them, I will put them to 1, because we can renormalize everything at the end, it doesn't matter. I just want to show you the algebraic tricks that leads to the solution of the equation. By the way, the equation, I forgot to remind you, the equation is always h bar psi is equal to derivative over time of x c time. But this is the evolution of our solution. But one thing that we can start looking are those solutions for which the energy is constant, and then we could see maybe in a later video how to evolve. Actually, we saw that already in a free particle moving, right? Because you can apply e to the IHT to our system to move it in time. So we have the Hamiltonian and we apply this exponential to move it in time, time 0, time t. So we can start always with an initial condition psi 0, our state psi 0, and that state can be with a defined energy, and this helps a lot to tackle many problems, and it's a standard way to proceed. So I will not be creative here, and I will just follow the main approach, which is very useful. and therefore I claim that I'm looking for solution of the kind that h psi is equal to one constant e, which is a number psi. Okay, this is technically saying that our if we measure our state with the energy, if we measure the energy of our state, we will get a precise value and always the same value in energy, which is E, which meaning that this means that we have a precise outcome. As we will see in quantum mechanics, there are superposition states. I will not talk about it today, but in later videos where the value is undetermined in some situation, and this is the essence of quantum. One of the main things in quantum mechanics is superposition, and the other is entanglement. We'll talk about these things in future, but at the moment we're just dealing with the easy things where we have a precise value for the thing that we want to measure, for the observer that we want to measure, and that is fixed in time. Okay, so our system, for example, is sitting in resting position, as the pendulum as before was sitting in the resting position. We have a value for the energy. We can write it down. We write the velocity 0 plus the position 1k, whatever position x square the pendulum has. If we cut the cord, that potential energy will transform in kinetic energy, for example. So there is some energy in a pendulum that is stuck hung on the wall. Just we don't see it in action. Okay, enough. So these are stationary state. We call them stationary state. Stationary states. And algebraically they're called eigenstates, but we don't go at the moment in those details. Okay, so the solution that we want to solve is this one, the equation that we want to solve. Okay, how do we do? Okay, we want to show a few things. Let's see if I can do this. Okay, so first of all, we want to notice few things about our operator A and A dagger, because we want to show A and A dagger commute with the Ni, like commutation A dagger is the identity. Okay, and this is because they inside them they have X and P that have the same commutation relationship. So this means that A dagger, A minus A dagger, as you can see, I swap the position of the two, is equal to identity. So when we swap the position, the order of the operation, the result might change. Okay, so let's see what happens. So we said already that our Hamiltonian can be written as A dagger A plus 1/2, let's say h bar omega, so a bit of energy. There was, and this is in fact due to this commutation. There is an identity here, because this is an operator, these are operators, and here is a number, so something odd. Ideally there should be an identity written here, but for easiness of to write down things easy, we just know that when there is a number, we are thinking about a number times an operator that is an identity. Okay, an identity is just a matrix that is 1 1 1 1 1 1 in all dimensions and 0 everywhere else. Okay, so the identity does exactly the multiplication on a vector identity V. You get V, identity matrix, you get the matrix, and whatever. So it's exactly like the number 1. If you do 1 times 3 is 3, 1 times whatever, pi is pi, and the same happens with operator. you have an operator that does nothing, or just in this case multiply by a number. So just because I don't want to carry over this operator everywhere, the same way we don't do it with the number 1 everywhere, I just cancel out the operator identity, and we remember that there is an identity there. But anyway, so now let's see what happens if we do this operation. H to the state a dagger, sorry, a dagger psi. What happened to this state? First of all, we are applying the operator a dagger to the state to see what it does to this whatever state we decide. A state psi is whatever condition our system is in. For example, we have the pendulum. In this case, it's a particle in a harmonic potential. Think about a pendulum, but in quantum mechanics, it could be a pendulum. Anyway, think about this particle in a harmonic potential, so this parabola here, and then we freeze it in time, and we know that the state of the system, so the properties, if we look at all the properties of the system, can be captured in one set of complex number. We call it psi. This is called the state of the system. Okay, literally how the system is in that moment. So what happens when we apply the operation a dagger? Let's try to do it. So we do a dagger a plus h. This is the Hamiltonian h, and then we have a dagger psi. Now I go I will go backwards, so from bottom to top. Hope you don't mind. And let's see if we can do some little algebra. So we got h a dagger psi, and this is so now this is a parenthesis with a plus, so we multiply this number times this, and we get a dagger plus a dagger h omega. I did nothing but multiplying the number, and now if I want to be more specific, I call this in red, so we trace the order of the operation. Okay, because we want to keep track of the operation, because we know that they don't commute. They have this weird this is called commutator, which means a dagger a minus. It's a compact way to write this this difference of operation. Okay, so now we have this oddly complicated structure. But we can see that we can do one easy step, which is extract the purple a dagger here and this one here and put them on the other side, and inside now we have this a dagger plus h omega psi. Now, as you can see, this is not quite as this one, right? Because the order of the two is different, right? But we know how to deal with it because we have this equation here. So we know that we can basically rearrange the order, adding one identity, meaning that I can go up. This can be okay. Maybe I messed up the may have messed up the unit, but anyway, A dagger A plus 1 plus H bar omega H omega. Nice. And this one is because I swapped the two numbers here, and I use this formula here. There is a 1 here, right? 1 times identity is 1. Okay. But now we see clearly what happens, because now we have that this is we can multiply psi. We get A dagger psi, which is our initial thing. Sorry, A dagger H H psi, because this one and this one are exactly H, as we know here. This was H, so these are the same, so we get the NH there, plus A dagger psi. Okay, so now we're done, because I can cancel the harmonic oscillator because we know what we're doing. Now we're done, right? Why? Because now H bar H dagger H psi, we use this equation here because we're using this stationary states that we talked about, which means E. So this actually means A dagger E, which is a number, energy, plus psi, plus A dagger psi. But now it's very easy because this is the same operator applied to the system, meaning that we have that H, we have that A dagger plus energy plus sorry, A dagger no, let me do it correctly. We need to, yes, energy plus 1. Here, A dagger psi, energy plus 1. Okay, so basically we are added 1 to the energy, as you can see. So because this is the same vector at the beginning, so what happens is that this vector here has an energy plus 1, while the initial vector here had only just energy. And this is important because we just showed that they are applying this operator to the energy will promote the energy by 1 bit, which is the minimum that you can do to increase the energy of the system. So you cannot do less than that. You cannot increase less than this amount of energy, and then you can see how to scale things up, because now what we're missing is that, and this, by the way, this is called creation operator as well, because it creates a quanta of energy in your system. So this operator is fundamental because it tells you that is the fundamental building block to populate your state with energy, to give your energy to your state. So what is happening now is that the energy of the system is increased by 1 on these states here. Okay, so we raise the energy, but in the same manner we can show that A dagger, we can doing the same calculation but with the other operator, we can show that if you use the A operator, not the A dagger operator, the energy will be lowered. So we will have psi energy -1, okay? Okay. Now, this should tell us something, because it means that we can find exactly this point here, if you think about it. Wherever, if we find this point here, the 0 point energy, we cannot go lower than that, because there is no negative energy, at least not here. So, all to say that we simplify the problem in understanding what is the minimum energy, minimum state energy. The ground state is called ground state. Ground state. The ground state is the state with the lowest energy, after which, below which you cannot go. Let's call it psi 0. How do we find it? We find it solving this equation: A psi 0 equal to whatever, 0. Okay, because when we apply the minimum energy and we subtract 1, we get 0, so 0 point energy. And this is an equation that we can solve, because this is x minus IP psi equal to 0. But we know that this can be written as, in operator, x minus the derivative of x, function of x, whatever function it is equal to 0. Okay. And then I think I will stop here for a sec, and then in the next video I will carry on this calculation to show you the ground 0, and from that we can then construct all the states of our harmonic oscillator and give some intuition of that. But let's pause here because it's quite long already. See you in a bit.